I am going to talk about what is radial and transfer component of velocity and acceleration, and I am going to derive expression for dr by dt, ds by dt, and expression for velocity in terms of radial component and transfer component, and expression for acceleration in terms of radial component and transverse component. So this is what I am going to do. In this video, we are going to learn the basic calculations for both obtaining both radial and transfer component for velocity and acceleration. Suppose we have a curve. This is a curve. Any shape. I have drawn this shape, but the curve can have any shape. And on this curve, there is a body. Suppose this is a body. And this body is moving on this curve in a particular direction. So this body, which is moving along this curve, will have velocity and also has the acceleration. So this velocity having two components and this acceleration also having two components. What are the two components of velocity? One is a radial component, another is a transverse component. Similarly, acceleration will have radial component as well as the transverse component. So when a particle moving along the curve, we need to calculate velocity, we need to calculate acceleration, and for both of them, for velocity as well as acceleration, we need to find radial component as well as the transverse components. So today I am going to tell you what is a procedure, what is a mathematical procedure to find the radial and transverse component of velocity and acceleration. Now denote the position of the particle by P and join O and P. Call it as a vector OP. So vector OP is the position vector of point P. P nothing but a particular position of the particle. And particle at not one place. The particle is keep on moving from one point to another point. It is not at rest. The particle is moving along the curve. And let us select a particular situation. And at a particular situation, the particle is present at the point P. Here, we are going to talk two direction. One is the direction OP. So vector OP, that is the direction of vector OP. Vector OP, direction of vector OP nothing but called radial direction. So it is a radial direction. And another direction we are going to talk about, that is perpendicular to OP. So we are going to talk this direction, and this direction is nothing but perpendicular to OP. Let us call it as a C. So PC. So PC nothing but perpendicular to OP. And this direction perpendicular to OP nothing but called as a transverse direction. So there are the two directions. One is the radial direction, another is the transverse direction. Now we can denote vector OP equals to vector R and vector S is perpendicular to vector OP. Yes, vector S nothing but transverse vector. One more thing, that unit vectors R cap is nothing but unit vector along R, vector R, and S cap is a unit transverse vector. S cap is perpendicular to vector R. So I am drawing here a vector perpendicular to vector OP. And in this direction, the vector S is there, and S cap is a unit vector along the direction of vector S. Now, let us say the vector OP is making an angle theta with the positive direction of x-axis. Now we can write expression for R cap and S cap. Now we can write R cap equals to cos theta multiplied by I cap plus sin theta multiplied by J cap. And S cap is being at 90 degree. So S cap equals to cos of 90 plus theta I sin of 90 plus theta J, which is equals to minus sin theta I cap plus cos theta J cap. So we got here the expression for R cap and S cap. In this discussion, R depends upon theta and theta depends upon T, as well as S depends upon theta and theta depends upon T. Now both R cap and S cap, there is a variation in R cap S cap with respect to time. R cap and S cap are changing with respect to time. Therefore, differentiation of R with respect to T and differentiating S cap with respect to T. So the differentiation of cos theta is minus sin theta, but theta is depending upon time. Therefore, differentiating again theta with respect to T, that is d theta by dt, I cap, plus differentiation of sin theta is cos theta, but theta again depending upon time T. Therefore, differentiating theta again with respect to T multiplied by J cap. Similarly, for ds cap with respect to T is nothing but minus cos theta, again differentiating theta with respect to time, so d theta by dt, and I cap plus minus sin theta, again differentiation of theta with respect to T multiplied by J cap. Here ds cap by dt, taking minus common as well as d theta by dt common, so we get cos theta I cap plus sin theta J cap, and we are again taking d theta by dt common, left side dr by dt, that is R cap, and again here taking d theta by dt common, so we get these expressions. Two expressions we got here for dr by dt and ds by dt. The term in the bracket minus sin theta I cap and cos theta J cap, this is nothing but S cap. You see this is the S cap. So here this minus sin theta I cap cos theta J cap is replaced by the S cap. Similarly, cos theta I cap sin theta J cap is nothing but R cap. So here replacing it by R cap. So we got dr by dt equals to S cap d theta by dt, and ds cap by dt equals to minus R cap d theta by dt. Let us call them 1 and 2. Here in this diagram, vector OP is equals to vector R, and let R equals to magnitude of vector R. So vector OP, that is equals to vector R, can be written as R multiplied by unit vector in the direction of vector OP. Therefore, vector r equals to r multiplied by r cap. This we are going to use to find expression for velocity of the particle, and we are going to find radial and transfer component of velocity. We have vector r equals to r multiplied by r cap. Now differentiating both sides with respect to t. Why we are doing differentiation? Because dr by dt, that is the rate of change of displacement, will give velocity. So to get the velocity, we are differentiating both sides with respect to t. So dr by dt equals to r as it is, differentiation of r cap with respect to t, plus r cap as it is, differentiation of r with respect to t, because both are r as well as r cap, they depend upon theta, and theta depend upon t. That means r depends upon t. Therefore we are using here the product rule of differentiation. So we got here dr by dt equals to r dr cap with respect to t plus r cap and dr by dt. Rearranging, we get dr by dt equals to dr by dt r cap plus r multiplied by dr cap by dt. So dr by dt writing as it is, r cap also writing as it is, and in place of dr by dt we can write s cap d theta by dt. In place of this we can write s cap d theta by dt. Therefore dr by dt equals to dr by dt r cap plus r d theta by dt, and writing s cap outside. But dr by dt is nothing but velocity vector. Therefore vector v equals to dr by dt multiplied by r cap plus r d theta by dt multiplied by s cap. Dr by dt, in this expression, dr by dt called as radial component of velocity, radial component of velocity, and r d theta by dt is called transverse component of velocity. In this way, we find radial and transfer component of velocity. Now, after finding radial and transfer component of velocity, now let us obtain radial and transfer component of acceleration. So we have already this expression for velocity, and to get acceleration is nothing but rate of change of velocity, that is differentiation of v with respect to t. Therefore, differentiating this expression with respect to t. So differentiation of v with respect to t equals to differentiation of dr by dt multiplied by r cap plus r d theta by dt multiplied by s cap with respect to t. This is equivalent to, so after differentiation and simplifying, I directly written here. If many of you request me to do the complete differentiation of this, then please write down your request in comment box. I will certainly do the double derivative as well as. Here I have directly written. So that after doing differentiation, I got in the first bracket d2r by dt square minus r d theta by dt whole square multiplied by r cap. In the second bracket, I got twice dr by dt multiplied by d theta by dt plus r d2 theta by dt square s cap, where d2r by dt square minus r d theta by dt whole square is called as radial component of acceleration, and twice dr by dt multiplied by d theta by dt plus r d2 theta by dt square is called as a transverse component of acceleration. In this way, we obtain the radial component and transverse component of acceleration.